Assalamu alaikum warahmatullahi wabarakatuh. And good morning, everyone. My name is Muhammad Naeem Mahyuddin, and I'm presenting my research entitled Evaluating the Strength Development of Ceramic Waste Powder, Silica Fume Geopolymer Mortars, Compressive and Tensile Behavior. Now, this study falls under the conference cluster of sustainable materials and technologies, and it is a collaborative work with my colleague from UITM Perak branch. So let me begin with a quick overview. We ask ourselves, how can we develop more sustainable construction materials without sacrificing strength or durability? Now, these led us to explore the use of ceramic waste powder, which is called CWP, and silica fume, SF. Now, two industrial byproducts in hybrid geopolymer mortars. CWP helps improve matrix packing density, while SF, silica fume, contributes to gel formation thanks to its high reactivity. Now, the goal is to design an eco efficient, high performance mortar that supports the circular economy. Okay, the construction sector is under growing pressure to cut carbon emissions. Ordinary Portland cement alone accounts for a significant share of global CO2 output. Geopolymers offer a low carbon alternative, but pure geopolymer mortars often suffer from inconsistent strength and sensitivity to curing. This research aims to address these issues by developing a hybrid geopolymer mortar using CWP alongside with SF with a minimal amount of cement to enhance performance and sustainability. Now let's see what are the core problems. While geopolymer mortar promise durability and lower environmental impact, their early age strength is often unreliable. Inconsistent results arise from poor mix design, inadequate curing, and unoptimized activator use. There's also a gap in existing research, especially on how CWP perform together with SF under different curing conditions. So that's where our study comes in. So we had a key objective here to evaluate both fresh and hardened properties of hybrid geopolymer mortars, analyze microstructure using SEM and XRD, investigate how CWP affects matrix density and how SF boosts geopolymerization. Okay, so the research methodology would be to use CWP, okay, and SF with a fixed 20% of OPC, and activator included NaOH and sodium silicate varied in concentration. So we tested 5 series with different CWP ratios that were subjected to 4 curing regimes, which is ambient curing, water curing, oven dried with a different temperature, which is the 70 degrees Celsius and 100 degrees Celsius. So our test covered compressive strength, split tensile strength, flexural strength, durability, and microstructure. So let's move on to the results. So the result shows that CW3 containing 40% CWP, 40% of SF, and 20% of OPC consistently performed the best. Okay. Under ambient curing, it reached around 24 MPa at 28 days. Under water curing, it rose to 27 MPa. Oven curing accelerated early strength, especially at 70 degrees Celsius. So, in contrast, mixes with high CWP or high SF alone, like specimen CW1 and CW5, perform poorly due to unbalanced reactivity or lack of matrix integrity. Now let's look on to the split tensile. Okay, so in terms of tensile strength, TW3 again outperformed the rest, reaching about 2.6 MPa under both ambient and water curing. This aligns with the compressive strength findings, indicating a robust balance matrix. Mixes with excessive silica fume, such as specimen series CW5, showed early gains but long term brittleness due to microcracking and poor interlocking. Right. As a conclusion, CW3 offered the best overall performance regardless of curing method. Water and thermal curing at 70 degrees Celsius significantly enhanced strength. This balanced mix achieved a reliable tensile to compressive strength ratio of zero point 0.1, an indicator of structural integrity. So the high silica fume alone was insufficient without granular support from CWP. This research demonstrates the viability of industrial waste materials in creating durable, eco-friendly construction alternative. Thank you for your attention.